In this video, we will discuss confidence intervals for variances and standard deviations. To calculate confidence intervals for variances and standard deviations, we use a new statistical distribution, the chi-square distribution, which is symbolized chi-squared. This is the Greek letter chi, spelled C-H-I, and it looks like a big curvy X. A chi-square distribution is found by calculating n-1 times s squared over sigma squared when random samples are taken from a population normally distributed, population whose variance is sigma squared. A chi-square variable can't be negative, and the distributions are skewed to the right. The distribution becomes somewhat symmetric for degrees of freedom approximately 100 or greater. Characteristics of the chi-square distribution. First, all chi-square variables are greater than or equal to 10. The chi-square distribution is a family of curves based on the degrees of freedom. The area under each chi-square distribution curve is equal to 1, and the chi-square distributions are positively skewed. Table G on page 782 gives the values for the chi-square distribution. These values are used in the denominators of the formula for confidence intervals. On the table, the left column denotes degrees of freedom, and the top row represents the area to the right of the critical value. Because chi-square distributions are not symmetric, two values are used in the formula. One is on the left of the table and the other on the right. An example, find the values for chi-square right and chi-square left for a 90% confidence interval when n equals 25. So to find chi-square right, we subtract 1 minus 0.90, and that's equal to 0.10, and then we divide by 2 to get 0.05. To find chi-square left, we subtract 1 minus 0.05 equals 0.95. We use the 0.95 and 0.05 columns with degrees of freedom n-1 equals 25 minus 1, which is 24. So here we have the 0.95 column and the 0.05 column. And here is the 24 row. And here are chi-square left and chi-square right, 13.848 and 36.415. If the number for the degrees of freedom is not given in the table, use the closest lower value in the table. Useful estimates for sigma squared and sigma are s squared and s, respectively. To find confidence intervals for variances and standard deviations, you must assume that the variable is normally distributed. So here are the formulas for chi-square for the confidence interval for a variance and the formula for the confidence interval for a standard deviation. Here, for the variance, we've got n-1 times s squared over chi-square right is less than sigma squared is less than n-1 times s squared over chi-square left. And the degrees of freedom for both of these are n-1, where n is the number of items in the sample. The formula for the confidence interval for a standard deviation is the square root of, each term is the square root of the terms in the confidence interval for the variance. So this is the square root of n-1 times s squared over chi-square right is less than sigma is less than the square root of n-1 times s squared over chi-square left. Assumptions for finding a confidence interval for a variance or standard deviation. First, the sample is a random sample, and second, the population must be normally distributed. round to one more decimal place than the number of decimal places in the original data. So for example, a study of 30 women found the standard deviation of their ages was 5.2 years. Find the 95% confidence interval for the age variable of the variance for the age variable. So first we assume, we want to assume that the variable is normally distributed. We have to assume that. Since alpha equals 0.05, the critical values for the 0.025 and 0.0975 levels for 29 degrees of freedom are 45.722 and 16.047. And we substitute the information we have into the formula. And then we've got 29 times 5.2 squared over 45.722 is less than sigma squared, is less than 29 times 5.2 squared over 16.047, which gives us 17.2 is less than sigma squared is less than 48.9. Remember, sigma squared is the variance. We don't want to take square roots here. We can be 95% confident that the true variance for the ages is between 17.2 and 48.9 years. It's a pretty big range, but you know. Now we're going to find the 90% confidence interval for the standard deviation for the number of named storms per year in the Atlantic Basin. Assume the distribution is approximately normal and we have a random sample of 10 years that we're using. And here are the values for those 10 years. So the first thing we have to do is calculate the sample variance, which is 16.9. And then we find chi-square left, which is 3.325, and chi-square right is 16.919. We plug these values into our formulas, and we're going to wind up with 3.0 is less than sigma is less than 6.8. So we can be 90% confident that the standard deviation for the number of named storms is between 3.0 and 6.8.